Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am very happy to have Conor Ransome with us today. Hello, Conor.
Hey, thank you for having me.
Well, thank you so much for agreeing to talk about your very lovely article. We'll get to that real soon. So it's very good. That is an awesome picture you have over your right shoulder there, the famous blue ball there.
Yeah, it was, I don't know if anyone knows the history of the recent history of the CFA here, but the library was closed recently.
Oh,
So I liberated this from the library.
thank you
Uh,
for saving that.
yeah, it now lives in my office. So
Very
here's the
cool.
balls.
Very cool. And speaking of your office, what's your geolocation, Connor?
I am at the Harvard CFA in Cambridge, Massachusetts.
Very cool.
Uh,
Let's see. Oh, go ahead.
no,
Okay. And it is September 26th of 2024 as we record this. So we're a little past equinox. And is fall in the air yet in Boston?
yeah, it's kind of gloomy. Colors are changing. Reminded me a little bit of home in old England, not New England.
Yeah, very
Uh,
cool. Good. Let's see. And I am in Phoenix, and we're definitely cooling down. We've gotten away from our big temps. Now they're only sort of big, but we're definitely cooling down a little bit. So it's really nice. Very cool.
what is cooling down for Phoenix, though?
Well, let's see. At peak heat in today will probably be about 103, 104 F. So, and if I do,
Positively chilly. Yeah.
yeah, very chilly. Yeah, man. Well, you know you're a Phoenician when it goes below 100 and you start breaking out your winter jackets. So you've completely lost any heat capacity there. So very cool. And what's your position there in Cambridge?
I'm a postdoc.
Oh,
Uh,
cool.
yeah,
Very
I
good.
work with Professor Ashley Villar.
Oh, very good. Very nice. And Connor, what do you like to do for research?
I mainly study interacting supernovae. So
Cool.
these are supernovae which explode inside a medium of some variety, whether this be something super extended or what we'll be talking about today, something much more confined.
Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. Go grab a copy for free. SN 2023 IXF in Messier 101, the twilight years of the progenitor as seen by pan-stars. And Connor, take us away.
Thank you very much, Fred. So first, I'd like to thank my collaborators. This work was done in the Young Supernova Experiment collaboration. This is a lot of really, really lovely people who have helped a lot with this paper. So I will just outline the collaboration a bit later on.
Okay, good
Uh,
shout out.
yeah. So I think to start off with, if we go down to figure eight, which is another big pretty picture.
Let's go down to figure eight, and I think we have a very lovely image. So let's take a look at this image. Bang, there we go.
Yeah. So
Yeah,
Supernova 2023 IXF, super nearby, around 7 megaparsecs.
mm-hmm.
This thing exploded. It was discovered by Koichi Itagaki in Japan. And this guy is a very prolific amateur astronomer. He
Indeed.
discovered a lot.
Yes.
Um, so the closest, one of the closest supernovae in the past decade. The previous closest was also in this host, M101.
Hmm.
Which is cool. And I just thought I would start with just this nice picture.
Yeah, lovely.
So this is a Pan-STARRS composite with a circle over the supernova location.
Boom. And here we are right at the edge. Yep.
Yeah. So that is an I-band image, and then there's a continuous attracted image in the bottom left, which I'll talk about later.
Ah, okay, cool. I'm
Mhm.
with you. Mm-hmm.
Cool. So if we go back to the introduction,
Sure.
I'll try to go through why we think this is interesting.
Sure.
Um, So with this supernova being so close, it was a type 2 supernova, so it was a hydrogen-rich core collapse. Um, it was, as I was saying, it's one of the very closest that we've seen. And the very early papers, so because this was so close, there was a huge scramble for to write cool things about this. And there were detections of the pre-explosion star in HST imaging.
Okay.
And these type 2 supernovae are sort of the more common progenitors that we see in serendipitous imaging. And yes, this one, it sort of created a scramble, and we have all these really big surveys now. So there's a bunch of pre-explosion imaging of just the site of where the supernova is. So there was a great effort in looking into the nature of the star. And another interesting aspect, which is just on page 2, past all the references there. Yeah, so a lot of people have worked on this and taken different angles.
Oh, yeah.
So because it was so close, initially any optical follow-up was actually quite difficult because the exposure times needed was so incredibly short before you just completely saturated your CCD. But one cool aspect, which is why I'm interested in this as someone who looks at interacting supernovae, is that the very early spectrum showed signs of interaction with a dense nearby circumstellar medium.
Okay.
And these are they're often called flash ionization signatures. And what this is when high energy photons from the shock breakout photoionizes this close-in material.
Yep.
And these things seem to be fairly common. So previous sample studies which look at CTF and these other large surveys, they find that around a third at least have these signatures. Maybe we will find more as we get earlier and earlier into these into these objects. So
good.
So we are interested as interacting supernovae people into this because the amount of material that you need as to if it was ejected, it had to have been ejected fairly recently in our frame of reference, very late in the later life of the progenitor, but within the past few years. Now these red supergiant progenitors, the canonical line-driven winds are too weak to be able to lose all this mass. So we really do think that there might, if this is a detached or semi-detached CSM, so sort of unbound from the star, we really do think that it must have happened in some more eruptive event or more violent superwind. So there are these different mass loss modes. So yeah, we think that this might happen at least in some of these objects. So one important object which we use as a reference here is the Type 2 supernova 2020 TLF.
Okay.
And one of my collaborators, Win Jacobson Galan, has a paper on this object, and he did find a precursor eruption, so an observable eruption at around -9 mag.
Interesting.
And whatever mechanism made this, whether it be some unstable burning or gravity wave pulsation or something, the theories out there on what it could be, but this happened within a few months prior to the terminal eruption.
Yes.
Okay. So there might be as much as a solar mass in the CSM.
That's a
I
lot.
will point, I will point out that there is a alternative hypothesis which has been brought out recently, which is that the outer layers of the red supergiant might be puffy. So essentially, you aren't looking at a CSM, you're looking at the outer layers of
Outer
the star
parts, yeah.
that's being photoionized, which might be a relevant piece of information as we go through.
Yeah, yeah.
So lots of people looked at this thing, and a lot of what we want to do is we want to get limits on any pre-explosion activity, and
Yes.
we want to look at the progenitor and see what the star was. So we know it was a dusty red supergiant, and another one of my collaborators, Charlie Kilpatrick, had a paper looking at the dust, um, and made an estimate of the mass. And then a lot of other people also did these things looking at the mass and where the progenitor star might lay on the Hertzsprung-Russell diagram,
Uh-huh. Yes.
or should I say like an evolutionary track diagram?
Yeah. Okay.
Actually, yeah. Yeah. So what we'll talk about first is how we use some new data. So a lot of what I do to try and characterize a progenitor is I look at all of the literature uh, values and all the literature photometry, and then I combine it with our new stuff from Pan-STARRS.
Got it. Cool.
So with the young supernova experiment, we have access to Pan-STARRS, and there's around a 5,000 day um,
Wow.
uh, uh,
Wow.
5,000 day pre-explosion baseline there.
There we go. Very cool.
So just before we get onto that, no one found any evidence of outbursts. And
Okay.
the so there's some limits placed on optical and limits placed on UV.
Okay.
No one found any sort of convincing pre-explosion outburst, but the progenitor was detected in at least the HST bands,
Yeah. Very cool. Nice.
which is cool. So yeah, so we'll go through the photometries. So for the young supernova experiment, the main aim is to try and catch these objects as early as possible.
Yes.
So we precede the fields of other surveys. So when they discover some transient, whether it be a supernova or whatever,
Hmm.
the idea is that we sort of preceded that field and should hopefully have
Nice.
something earlier, or at least a limit on the explosion time.
Cool. Cool.
Um,
Yep.
but also through this collaboration, we have a bunch of pre-explosion imaging.
Hmm.
So there was around 300 epochs of, of imaging in Pan-STARRS Grizzly filters. We
Nice.
also looked at the W filter. Now, Yeezy doesn't usually look at the W filter, and this is because there is no color information.
Ah, okay.
Um, but Pan-STARRS uses it to look at asteroids, essentially. So we had that for free.
Yay.
um, yeah, so that's cool. So we use a slightly novel because even though this is close by and it is a fairly luminous star anyway, it's
Yeah.
still dusty and it's still extragalactic. So we try and get as deep limits as we can because
Yeah.
then this helps us put constraints on the SED that we're going to try and construct later.
Okay.
So I will briefly go through our detection pipeline because it might be a little bit different to what people are used to.
Unusual. Yeah.
Um, so essentially what we do after the data reduction is that we use artificial star injection to try and uh, get as deep limits as we possibly can. So what this involves is that we we have our reduced image, our processed image, and we construct apertures for force photometry, essentially.
Hmm.
And what we do is we match the pixel distribution to fairly tight constraints for the region that these apertures are in. And we want to match that to the supernova site because
Yes.
when you have these difference imaging, these difference images,
Hmm. Hmm.
um, there might be some sort of non-Gaussian noise
Oh, so,
that we want to try and account for
yeah.
in this sort of algorithm that that people have come up with in Yeezy. So
Cool.
we take these images and we match the distributions, and then we essentially insert artificial stars into all these apertures.
Okay. Bing, 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 bing,
Uh,
bing.
yep. And then we make them brighter and brighter and brighter until over 80% of these, which is it's a moderately arbitrary cutoff, but it is kind of what's done.
Okay.
Uh, until 80% of all of these sources are over a 3 sigma detection limit.
Okay. Okay. I'm with you.
And then we sort of call that our limit there. So yeah, then we then compare all of our actual um, supernova force photometry to the limit that we get from this.
Yes.
And this is summarized in the first table. Um, so we did this with individual images, and then we did it
Yeah.
with stacked images, and the stacked images get a little deeper. Um, to summarize this, we do not find any convincing detection in these pan-star optical images.
Okay.
Um,
Mm-hmm. Mm-hmm. There's our W. Mm-hmm.
so we're pretty deep into view, but that's because it's a very broadband filter.
Mm-hmm.
It's sort of like a white light filter. Um, Yeah, so the number of apertures you might see change. That just changes depending um, on how many apertures are matched. We use at least 10 though, so we have
Okay.
a decent
Decent number.
yeah a decent number for this. So we get some fairly decent limits on these
Okay.
around sort of minus 5, 6 um, on any pre-explosion like progenitor detection. Um, so there was no sort of like really obvious activity in the optical
Okay.
of this object. So if we just go to the big light curve figure next,
Yeah.
this is all summarized there.
Gain of evidence. That's what we saw. Very good. Let's take a look at figure one. There we go.
Yeah. Okay.
Okay.
So there's a few things here
Mhm.
that I'll go through. So this is composite photometry taken from the other papers, going from sort of the near IR, and then we also have Spitzer. Now, what you might notice with the
Yes.
Spitzer is that there is some variability,
Yes. Hmm.
um, and that there are
Yep.
detections in the longer wavelengths. So, like J, and I think there's like K band and H band as well in there somewhere.
Yes.
So this is, we think this is a super dusty thing, um,
Okay.
which is why we have these very red colors.
Good
And,
choice.
and this variability, so Charlie Kilpatrick
Hmm.
interprets this as Kappa mode oscillations. So it's like a pulsation in the stellar atmosphere. Yeah.
Yep. Yep.
Um, So that's what that is
Okay.
good. And you sort of see that in the very last, I think those are MMT, MMIRS, J-band points. Like
Yeah, these
it's
blue
squint
ones.
a little bit, you might be able to see a little bit of of a period there, which might match up with the Spitzer stuff. But there's
Yeah.
not too much of that. But there's a decent amount of Spitzer though, which is pretty cool.
Yeah.
Um,
Very nice. Beautiful.
yeah. So we have all of these upper limits in sort of transparent points, transparent triangles.
Mm-hmm.
In optical, we don't really see anything. And what I want to talk about are these horizontal dashed lines. So
Okay.
these are the pre-explosion, uh,
Okay.
the pre-supernova explosion. Actually, no, I'm lying. Just the precursor eruptions of these different objects. So first you have 2020 TLF, which is WINS object. Um,
Ah, very good.
uh, and all of our points are below all of these, even the limits in bad weather.
Ye-
Um,
yes. Mm-hmm.
and then you have 2011 HT, which is an example of a Type 2N. Now, Type 2N supernovae are what I usually study, and these have very extended CSM, and the interaction lasts a lot longer than these flash ionization things. So, with a flash ionization supernova, the interaction signatures will have gone within a week or so.
Yes. Okay.
The ejected
Get it
spectrum.
early. Get it early. Yep.
Yeah, yeah. Um, and then you have in these type 2N supernovae, these precursor eruptions are also pretty common. And this is because we think the progenitors of those are LBVs, which have these big giant
Mm,
outbursts.
yeah.
Yeah. And these look like in some cases also look like supernovae, just very dim supernovae, which is what 2000 CH and 2016 BLU are.
Mm-hmm.
So these are what we call supernova imposters, which are giant eruptions of luminous blue variables.
Mm-hmm.
Uh, so I believe both of those are actually periodic due to binary interactions, which is pretty cool. And
Very
then
cool.
at the very brightest there
Yep.
is the 2009 eruption of 2009 IP, which is another 2N. It's a very well studied 2N. So we think that this one actually properly exploded in 2012. So you had this um, fairly bright precursor, and
Mm-hmm.
then it sort of heralded a bunch of other eruptions, and then it finally exploded. Um, so these are the sort of objects that we want to compare to when we're
Okay.
talking about these precursor eruptions, or when we think that there might be some precursor eruption.
Cool. I'm with you.
Um, so another thing that I want to talk about on this plot, so there's around a 5,000 day baseline. There are a few gaps in there, here and there.
Mm-hmm.
Oh,
Mm-hmm.
at the bottom here, I'm trying to demonstrate that there are 2 points. There's one in Y and one in I, both Pan-Stars filters,
Yes.
uh,
Okay.
where our algorithm does say that there is a detection, and this is just by chance. You'd get this in uh, any sort of thing. It's just statistics, right? So
Mm,
we're trying to convince you, trying to convince the reader that there isn't actually anything there, or there's nothing super convincing there.
right. I'm
Yeah.
I'm convinced. Okay.
Mhm. Yeah. So we don't think that we saw anything in the optical. So what we now want to do is,
Okay.
if there was some precursor, how bright could it have been? And could we have actually seen it?
Right.
Sort of in our limits, like, can we sort of eke it out there in some way? So if we just carry on going a little bit down, please.
Sure. Uh-huh.
Yeah.
Now stack.
Ah, yeah. So we'll talk about the progenitor analysis first. Sorry. Yeah. Um, so we have all of our stack limits that we looked at in table one, super deep optical limits. And this is where we combine them with
Yes.
uh, the photometry from other papers. So there's
Okay.
stuff from HST, there's stuff from MMT, sort of going from shorter bluish wavelengths up to the near infrared.
Huh.
Um, And the only detections we have are in these long wavelengths. So we use the limits in this SED fitting. So
Okay.
um, and one thing I should mention is that different papers treat the variability in the IR in a different way.
Okay.
So what we do is we sort of take a median of everything and treat that as sort of an average,
Okay.
as an average data point for those data.
Okay.
Yeah.
Cool. Okay.
So
I'm with you.
uh, we take mist models. So these are evolved um, uh, yeah, Marx models, I should say. And we
Oh.
combine them with Dusty, which is, so because Dusty, we want to evolve this, we want to see how things look like uh, behind a bunch of dust, essentially. So these are uh, radiative transfer codes, which look at uh, your star, your evolved. I think these models use a 15 solar mass red supergiant.
Yes. Uh-huh.
Um, and you can keep things as a free parameter, such as the luminosity and the temperature, the surface gravity. People tend to set as zero. Um, and then we also look at the optical depth of the dust because we know that this is fairly high. So when we do these fits, we find a log luminosity of around 5.1. We get a optical depth of around 8, and then our temperature is around 3900 Kelvin, with a dust temperature of around 400 Kelvin.
Mm.
Um,
Okay. Right about here. Mm-hmm.
so this sigma here is a white noise parameter that we add in.
Okay.
And what this does is
Wow.
it looks at uh, underestimating the noise. So if we've underestimated our error bars,
Yeah.
this sigma parameter will uh, increase our scatter to try and
Uh-huh. Okay.
accomplish this. We have a very low value on this, so we're pretty sure that we're quite confident with our uncertainties on the data points. So we try two different dust modes.
Mhm.
So we look at carbon-based dust and
Yes.
we look at silicate-based dust.
Good.
Um, we get a much brighter and hotter progenitor with silicate dust, and our reduced chi-squared isn't as favorable as uh, as the graphitic dust.
Okay. Cool.
Um,
Cool.
so the makeup of the dust has been used by some authors who found a lower mass to suggest that there might have been some electron capture supernova
Ooh.
uh, kind of thing happening here,
Ooh.
uh, which show a lot of carbonaceous dust, but that they require the very lower mass ranges here, which we can talk about later, show the scatter that everyone's finding. Yeah.
Cool.
So then what we do after all this, I go through the values that other people get. We are mostly consistent with the values in the literature.
Cool.
Um, and then what we want to do is that we want to look at um, where the progenitor that we have found in this modeling, where this sits on evolutionary tracks and see how that compares with the other papers.
Mm-hmm.
I think if we go to the next
Figure
figure.
that's going to be this SED. Yep. Surely is.
Yeah, so figure two, we're just showing our SED fit. Um, so this orange line is sort of our median fit,
Okay.
uh, and then all of these sort of transparent grey tracks are just Walker chains from our Bayesian fit.
Got
Uh,
it. Okay.
uh, so we have detections on the bluer side from HST.
Yes.
And these go up to the HJK
Mm.
bands. So we also sort of average together the bands from different instruments as well, to try and eliminate this IR variability that we're looking at.
Yeah,
Which is sort of why
like
the
bugs
amounts
too.
are a bit chunkier in the
Yeah,
IR. Yeah, we have our limits, so we're all below our limits, which is reassuring.
nice.
Um, and then we go up to these Spitzer bands as well. So it's Spitzer 3.6 microns and 4.5 microns, I believe.
Yeah, looks like it.
Um, yeah,
Log scale
uh,
here. Uh-huh.
and I think some of the Spitzer data was taken in the warm Spitzer and when Spitzer still had cooling.
Ah,
Um,
okay.
yeah, uh, cool. So that is our SED fit,
Very
uh,
nice.
which, just to summarize, has our band stars data and then takes everyone else's data as well. We
Mm-hmm.
treat the variability in the IR in a slightly different way. Um, and this is what we find. We add some dust and then um, see what we have. And we get a very reasonable, fairly massive star. So in uh, in the next figure,
Well, figure three. These look
yeah,
like
figure three. So
star
these are
tracks.
our evolutionary tracks. So these are the mist tracks. Sorry,
Mm-hmm.
I confuse my acronyms sometimes.
Oh, I do it all the time.
Yeah. So
All right, so we have a little somewhere in the vicinity of
so
20-ish.
these are we just have sort of equally spaced uh, masses here.
Mm-hmm.
The grey squares are previously observed red supergiant uh, progenitors from Stephen Smart's paper taken from the literature.
Mm-hmm.
Um,
Shout out Smart. Yep. Mm-hmm.
mhm. And then this big red star
Yep.
is our object. This is 2023 IXF. So what we're looking at here, it's not so much the temperature axis,
Yeah.
and this is because at the very end of a star's life, it sort of changes its color. It does wild things. You don't quite know where it will be. So what people tend to do is we look at the end of these evolutionary tracks in luminosity on the luminosity axis and see where we sort of overlap with the endpoints of
Okay.
these
Yep.
tracks.
Okay.
And what this tells us is that for this luminosity and this luminosity, um, what masses of stars might have zero age mass stars might have
Sam's.
produced
Right.
super.
Sam's mass. Mm-hmm.
Mhm. And what we find is that we have a range of between uh, 14 solar masses and 20 solar masses.
Mm,
Now,
okay.
14 solar masses is sort of a very um, ordinary range. The 20 solar masses range, it can sort of it bumps into this territory of the red supergiant problem where we don't really see these massive things. But
Right.
um, various all authors have written about why this might not be an issue. So it might just be a small numbers effect. So Emma Beezer has argued, who's currently at Arizona as a Bok Fellow.
Uh-huh.
She um, she argued that it might just be a numbers thing. It might not be a huge issue. So
Okay.
the red supergiant problem might not exist, but we need more data points. Cool. So
Always.
the next the next figure, yeah. So here we just compare with everyone else.
Mm-hmm. Cool.
Um,
Mm-hmm.
so
Mm-hmm.
these are all the papers that are looking at just the progenitor, which is
Oh,
crazy for this subject. Like, it's been so much attention. Like I don't know if you know, but at the New Orleans AAS meeting, there was an entire session just on the supernova.
I was at New Orleans. Yep. Mm-hmm.
Yeah, and that was so much fun. I got to present this paper there. It was fantastic.
Very nice.
So here we have everyone else's. At the time of writing, there have been,
Yeah, sure, sure.
I think there's a few
But
more
it is
now.
recent.
Yeah, it is recent.
We're yeah, April of 2024. We're doing good.
Mhm. Yeah, so this is again with a red star, and we're
Yep.
in the middle of the pack. So we have
Indeed.
yeah, so we're very consistent with the vast majority of people. Um,
Hmm, okay.
yeah, Charlie Kilpatrick found a fairly low mass red supergiant. He
That's yeah.
doing things slightly differently to us. And then the very first paper on IXF that came out was Joanne Pledger,
Hmm.
who
Yep.
looked at uh, just HST images
Yep.
that are not on this plot because I don't think they had a temperature. They just had
Uh,
a luminosity.
luminosity. Yep. Yeah.
Mhm. Um,
Yep.
so they found a very low mass, but there's a bit of a scatter. I think the scatter goes from 10 solar masses all the way up to 24.
Yeah, that's a healthy range. Okay.
Mhm. Uh, so that pretty much covers the range of red supergiants, nearly,
Pretty nice. There's at
which
least a
is
lot of
fun.
them.
Yeah, yeah, yeah. So this is interesting, and we have a few later papers which now we have like the evolution of the actual supernova
Yeah.
and nebula spectra. There have been
Right.
there's been more work into this, but people sort of do get this middle ground, sort of 15 solar masses, which is
Okay. Converging, converging.
yeah, slowly converging.
Hmm.
So
Cool.
the next part of what we wanted to do here
Okay.
was, as I was about to say earlier, but I jumped the gun a bit, is that we wanted to put constraints on any possible uh, precursor eruption.
Okay.
So what we did is that we used a machine learning technique called a
Mm.
multi-layer perceptron.
Mm.
And what this is a type of neural network, which is often used for classifying things. So what you do is that you make a training set, whether this is on data or if it's on a model.
Yes.
So what we do is we take sort of an Arnetti style model um, made by one of the co-authors, Anna Tartaglia, who has just started here at Harvard as a grad student,
Hey, good
uh,
job.
which is cool. Um, and we take this model and then we take our data and could you just scroll down to the model so I remember what parameters we have?
Yeah.
Yeah, yeah. So we have the ejector mass, sort of the star radius. We fix we fix the opacity, and then we have the time along our baseline,
Before.
the input luminosity. Um, so what we're doing is we are just
That long. Hmm.
somewhere in the data we are making an explosion. We're not entirely sure how these precursor events necessarily happen, but what we're doing is we're trying to look for if we see them essentially.
Yes.
So we assume this model. Uh, we assume a wind velocity. So uh, with fairly high resolution
Yeah. Okay.
spectroscopy, you
Hmm.
look at your narrow feature in
There we go.
that we talk about this interaction signature. It's the narrow feature. We usually look at the H alpha because these are hydrogen-rich things. Um, you get the width of that, and that is roughly your CSM velocity. Um, so we fix it to around 50 kilometers per second, which is
Okay.
it's kind of sort of on the fast
Yeah, a little on the fast
uh,
side.
for red supergiants, but
Says even
some
more.
other papers have found that this is sort of like radiatively accelerated, and it might be a little bit slower than this, sort of around the canonical 10 kilometers per
That
second.
one's fixed. Okay.
Uh,
That's four.
mhm.
Okay.
Yeah, so we have this model, we make a bunch of training sets.
Hmm.
Uh, So we vary our ejector velocity and all these three parameters. So we go from 0 to around 1 million solar luminosities for our input luminosity.
Okay.
And this is of the order of the previous um, regular type 2 supernova outburst at 2020 TLF.
Mm-hmm.
Um,
Right.
we have our ejector mass going up to 1 solar mass
Okay.
of the precursor of the
Sure,
supernova.
probably not zero. Okay.
Uh, and then we have the progenitor varying between 1 solar radii to 1,000, which is sort of your very big puffy red
It's a
supergiant
very big one. Mm-hmm.
range.
Okay.
Yeah.
So lots of parameter space to explore. Okay.
Yeah, for sure. Uh, so we train around 10,000 light curves
Okay.
as our training set.
Okay.
And then and then because we didn't see anything, what we want to do in a similar way is see what set of models for varying. So sorry, I'll backtrack slightly.
That's
So,
okay.
so we have these 10,000 light curves
Uh-huh.
with these randomized parameters, and these made into a training set. So
Okay.
in machine learning land, these make up a part of your latent space, which is sort of a post-transform area of mathsy nonsense space almost.
Uh-huh.
Uh, and, and with your machine learning, what your network is doing, I should say, is that it's looking where your like sort of like new inputs fall in that latent space and see if it can be classified as belonging to uh, different spaces.
Yeah.
So
Okay.
um, we have
Okay.
this training, and then um, we then make another set of light curves where we fix. So, for example, we will fix the input luminosity or the ejector mass, and then randomize every other
Every other.
parameter.
Okay. Mm-hmm.
And then what we can do there is we can put those into our classifier, and then we look at the proportion of these that are classified as being detected
Okay.
or as being
Space.
uh,
Mm-hmm.
in our space and observable, essentially. Not observable, but being classifiable. Um, and using this, um, we can put constraints on the luminosity uh, and on the ejector mass as well.
Yes.
Around 50,000 solar luminosities. So this is
Okay.
twiddles
Sure.
around -7 mag, I believe.
Mm-hmm. Yes.
And with the ejector mass, we put a constraint of less than around a third of a solar mass.
Okay. Yes, there we go.
Yeah.
Uh-huh.
These are fainter than TLF by about 2.5 mag.
Yeah.
Uh,
Let's go down to
yeah.
figure 5 here. This is related, I think. Let's go. Here we go. Figure 5, right here.
Yes.
Bang.
Yes. So this is all summarized in figure 5. Um, yeah. So the top left panel,
Yeah.
these are our uh, set of models that are just training in luminosity.
Mm-hmm.
And this is just a kind of like a representative version of what's happening. These aren't necessarily the light curves that went into the work. This is just to show what the models do. And then
I'm sorry.
sorry, I'll get to the blue
Okay.
line.
Okay. Okay.
And then on the right are uh,
Mm-hmm.
the blue lines are a couple of hydrodynamical
Okay.
uh, outburst models made by Daiichi Tsuna.
Cool. Okay.
Um, we plot these as comparison, and we also have a we also try to find this in our data and make training sets up for this as well. We don't find uh, anything like these models either.
Okay. All right.
Mhm. And then the horizontal
Yeah.
dashed lines, these
Mhm.
are so the gray ones, so the one at the top,
Yes.
this is where 2020 TLF would have been.
Ah, okay.
Um, and then the the black one is sort of our limit.
Gotcha. Right.
What
Yeah,
we
we're below that. Yes.
yeah.
Yes. Okay.
And the way we come to these limits is shown on the bottom panel
Okay.
here.
Oh, there we
The
go.
bottom 2 panels. So we look at classification efficiency. So this is when how many of these light curves for a given set luminosity or ejector mass are classified as sort of it being in this training set
Yeah.
kind of thing.
Yes. Got it. Okay.
Um,
Uh-huh.
and then
So, wow. Okay.
mhm. So this all takes the same form as our data, so with the gaps and everything as well. Yeah.
Okay.
Um, so we
Okay.
take a similar cutoff to what we did before, where we say over 80% classification, we detect that we say this is detected.
Yes. Yes.
Uh,
Important to remember
and,
that.
and, and,
80%. Mm-hmm.
and this is where we get this 50,000 solar luminosities from. And then also plotted there is what TLF was like as well.
Okay.
And then the right panel is the same as the left, but for ejector mass. So this is the 80% classification of the
Got it.
ejector
Same
mass.
y-axis. Okay. Uh-huh. Uh-huh.
Yeah.
Okay. Here again. Get down. Okay. Cool. I'm with you.
Mm-hmm.
Okay.
Cool.
Nice
Yeah.
figure.
So
Nice figure.
we use this work to put this limit on any possible outburst.
Mhm.
Um, so no one has found an outburst, and these outbursts in regular type twos seem to be kind of rare. Really, we have 2020 TLF, but then we have a lot of these objects which show the flash ionization.
Yeah.
What this could be is um, what I was saying earlier with these inflated envelopes in these red supergiants. So observed um, there is no observed outburst because there hasn't been an outburst.
Okay.
Yeah.
Good.
But we know that some of them do have outbursts.
Some
So
of them do. Yeah, 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 yeah. Okay. I'm with you. I'm with you. Yeah, yeah.
yeah, so it's cool. We also briefly looked into the variability,
Yes.
which is the next bit. So we were wondering if you could get if the optical if the optical data also followed this uh, infrared variability that we're seeing,
Right. Right.
uh, because if you assume like a constant bolometric luminosity and your IR is changing, there might be sort of an anti-phase thing in the optical.
Maybe. Yeah.
Uh, so
It's hard to believe.
again, we used this classifier, and we essentially made sort of various different varying light curves. Again, we made 2,000 of these things. And again, we didn't actually see anything. So I think this is
Okay. So it's consistent.
completely consistent with what we're finding. So I
Yeah.
think the next lot of figures shows the
Oh,
variability.
yeah. Okay. Sorry. Figure six. Pre-explosion.
Yeah.
Stability.
So figure six, this is looking at how things change depending on how we assume
Okay.
it is happening. So the red triangles are just our photometry points. so these are our limits.
Yes.
And then if it is the temperature and luminosity that is driving any oscillation, then this is
Okay.
um, the yellow crosses. And
Yeah.
then if it's the dust that is doing this, or the opacity,
Okay. It's down. Up below.
then
Uh-huh.
then these are the grey squares. Uh,
Mm,
but we sort of find everything is just consistent with our photometry,
yeah.
um,
Especially
more or less. Um,
yeah.
yeah, and what we also did is we wanted to see uh, sorry, the next figure also
Oh,
shows
sorry.
us
Okay.
changing. Um,
Uh, this is scatter. Okay.
yeah, yeah. So this is again, this is trying to find any optical variability. So you can easily see the Spitzer variability in this one. It's very bright. It's sort of purpley and greeny points there.
Yes, channel one, channel two.
Mhm.
Mm-hmm. Right.
And then
Oh yeah.
also you can see sort of
Oh
the
yeah.
ground-based infrared stuff later on as well.
Okay.
Um,
Okay.
and what we did is that we wanted to see how much sort of like extra noise you needed to add to get a perfect chi-square to match this
Okay.
delta zero point essentially. And we found that there might be some kind of marginal variability, but I wouldn't make any super strong claim.
Well, yeah, I bet the house on that one. Okay.
Mhm. So we
Well,
don't really claim that we observe any optical variability here.
yet. Okay.
Uh, yeah, so to
Spectacular.
summarize what we've talked about so far, um, we have found a dusty red supergiant.
Yes.
We've found
Okay.
uh, a red supergiant that is between 14 and 20 solar masses. This is
Mm-hmm.
very consistent with what previous studies have found and studies that have come after. Some nebula spectrum analyses have found something a little bit less massive, but then light curve modeling papers have found something sort of in this 15 solar mass range. So
Cool.
there's still a scatter happening. So we also don't see any outbursts or any variability. So the last thing that we do is we briefly look at the host. So this is where we go back to
Go back to figure eight. Yeah, yeah. What we started with. Uh-huh.
yeah.
Okay.
So in this figure, this is a composite band stars image.
Yep.
Um, White circle showing us where the supernova is. In the top right, I think this is a Pan-STARRS I band image. So it's obviously a crowded field, and it's sort of on the edge
It is.
of a spiral arms star formation region.
Yes.
One of the things that I'm interested in is the host galaxies of supernovae. Because in lieu of progenitor, even though we have one here, in lieu of progenitor detections, the host galaxies can tell us quite a lot um, about the stellar populations that these supernovae are happening in. So far, it's on a spiral arm, extremely standard core collapse
Yeah.
region.
Yeah.
So then I use a technique which I used extensively during my PhD, which was developed by one of my supervisors, Phil James at Liverpool, and
Cool.
also used a lot by one of my other supervisors, Stacey Abigan Mawson,
Yeah.
which is a pixel statistics technique known as normalized cumulative ranking.
Ooh, okay.
And what this is that you take, uh, in this case, an H alpha image, so narrowband H alpha,
Okay.
narrowband image. You then scale these images, you then scale the R band to the H alpha image and take off the R band image from the H alpha image. And
Ah,
what it does is that it takes off the R band light from the H alpha light. And then what you can do is you can
okay.
do a cumulative ranking of all the pixels in your galaxy.
Okay.
And this ranks the association to H alpha. And the reason why we do this is because we expect the H alpha emission to be tracing ongoing star formation.
Yes. Okay. Okay. Yeah.
Um,
Yeah. 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 Yeah.
uh,
Got it. Got it. Got it. Cool.
and you can make NCR distributions. And when people look at, so Joe Anderson, who is at ESO right now,
Hmm.
Uh, he has a 2012 paper where he looks at different types of supernovae, different classes of supernovae, and makes a what we call a mass ladder in terms of progenitor masses. So things that we are pretty sure are from really massive stars follows a one-to-one distribution. And then we also have these type 2s, these type 2p type things.
Yeah.
And what we find is that the value that I get for this this host is like 0.26 or something.
Okay.
And this is almost exactly the median of the sample
Okay.
of twos. So this is without going into IFU, spectroscopy or anything, this is a super standard
Yes.
environment
Okay.
in
Nice.
totally what you
Good to
expect.
check that. Good to check that.
Yeah. Completely what we expect. So yeah, in summary, I'll probably summarize now. Using all of the available archival data that we had at the time,
Hmm.
uh, we got the deepest limits with the band styles data that we could using a very novel source injection technique.
Uh-huh.
Uh, and then we also use all this archival data with fitted, and then we fit SEDs to Marks and Dusty models, and we find a 14 to 20 solar mass red supergiant in a bunch of dust with a optical depth of around 8.
Yes.
Um,
Hmm.
we, uh, we used a neural net to put limits on any possible precursor eruption, even though we didn't see anything. We then didn't find any eruption in our data, and then we put limits of around 50,000 solar luminosities on any possible outburst.
Okay.
We then did the same for uh, models from a hydrosim from Daiichi Tsuna and didn't find anything. And
Uh-huh.
then we also looked at any variability, and we did not find any convincing variability. We put limits of the peaks of variability at around 40,000 luminosities,
Okay.
uh, and also is in a very, very standard environment for type 2 supernovae in
Yeah.
its host.
Cool. Very cool. Beautiful. Beautiful. Connor, I want to thank you so much for walking us through your very awesome article.
Thank you for
Very nice. Very
having me.
nice. Very cool. I mean, you kind of touched on it a little bit at a couple of points. Uh, so let me go ahead and push on that a little bit and ask, where do you think we go given the published article? Is there more data from different telescopes to mine out so that there's, 14 different things to compare with? Are there other wavelengths that might be interesting? Is there a need for different models? And just sort of next steps, where do we go on this particular supernovae?
Yeah, it's a fantastic question, and I think there are lots of different routes that people could go down. So there are a bunch of different precursor models that are coming out. So um, Tatsuya Matsumoto has come out with a bunch of precursor models. Uh, Other people are coming out with different models, assuming different things. There might be something coming out, something to do with binaries.
Yes. Okay.
Yeah, everything is binaries.
Yeah, right,
That's
exactly. Once you open that Pandora's box.
yeah. In terms of extra observations, so looking
Yeah.
at the uh, super late time things, people have already looked at the nebula spectrum,
Hmm. Hmm.
and because the nebula spectrum of a supernova can tell you about the progenitor star.
Hmm. Yeah.
Um, but then also what we can do if we still think that there might have been sort of this eruptive mass loss, is that you could look at longer wavelengths at the radio and then look at late time, and then you could maybe detect sort of the ejector then interacting with some material that's much further out.
Yeah.
And then in terms of other objects, so if these things
Ooh.
are fairly common, um, we have our current large surveys, and then I can't get away from this without talking about the legacy survey of space and time at the Vera C. Rubin Observatory, which it will be hopefully, knocking on wood, they'll be coming online next year.
Okay.
And this will be finding orders of magnitudes more transients than what we're finding
Yes,
now.
it will.
Um, while it might not necessarily find things as early with the cadence as we want,
You get a few. You get some.
yeah, we'll just have very large sample numbers. So I think we'll build a cool sample from that. Yeah.
Very nice. Maybe we'll find similar objects. So we can do some comparison stuff between.
Well, yes. So when IXF went off, though, it was called a once in a career supernova. 6 months later, another one went off, 24 GGI.
Yeah,
So
yeah. You've
yeah,
got two careers. That's two careers. So there we go. We can hope for 3 or 4 or 5.
yeah. This is time to main astronomy. Be quick. Uh, look at lots of different wavelengths and get spectra of everything.
Very nice. Very cool. Well, it'll be really fun to see this develop over the next couple of years.
For sure.
New models, and particularly as LSST comes online, it'll be very, very exciting to see. Very nice. Connor, thank you so much once again.
Thank you very much, Frank. Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.